Welcome to our 15th unit of the year, Solutions. So starting off, our first unit, or our first section of this unit, Concentrations of Solutions. So first of all, make sure we're comfortable with the terms. Solutions are made up of two parts. The solute particles, which oftentimes will be the salt that we're dissolving. So you think of table salt, sodium chloride, and NaCl. That would be your solute particles. And then the solvent, which is almost always water. So when you combine solute with solvent, you get your solution. The concentration of a solution is a lot of what this particular chapter is about, working with different concentrations of solutions. The concentration measures how much solute per solvent. A couple of terms you're going to hear quite often is dilute and concentrated. A dilute solution has a very small amount of solute dissolved per solvent, whereas a concentrated solution would have a lot of solute per solvent. Now, in chemistry, we don't necessarily love the terms dilute and concentrated. We use them, but they're qualitative terms, and we much prefer numeric values. So for instance, I've got two beakers here. Clearly one of them is more concentrated than the other. We can see that with our eyes. But if I have a third beaker with even more solute in it, now all of a sudden my once concentrated solution now looks dilute. So which is it? Is it concentrated or is it dilute? And in chemistry, these qualitative terms aren't always great. So we prefer a more quantitative approach. And there's going to be two types of quantitative concentration measurements we'll make in this class. First, we'll look at percent concentrations, and then also molarity, which is symbolized with a big M. Percent concentrations. There's going to be a couple of different percent concentrations. If you pay attention to the question, the way it's asking it, or the variables that they give you, I think you'll have no problem figuring out what type of concentration you're looking for. So the first type would be a percent by volume. And this is an amount of solute per volume. So you'll usually see the volume here, percent volume. And this is usually when you have one liquid dissolved in another liquid. Pretty simply, you do your percent volume, you do your volume of solute divided by your volume of solution times 100%. Your parts out of a whole, like any other percentage. Probably more commonly, we'll also have a percent mass to volume of a solution. And this, just like it says, compares a mass to a volume. So again, you're going to see that little m over a v. And this is your mass of solute over the total volume of solution. Generally, a little note here, generally we use milliliters as our volume for our solutions. I say generally, sometimes I see liters, sometimes you see other units, but generally we're looking for milliliters. I think the big thing, especially with percent by volume, is make sure whatever unit you're using, you use the same unit both times. Let's take a look at a percent concentration example. All right, back to the images we're looking at. Let's put a quantitative mark on these two. So let's say we've got these two beakers, and each of these dark blue dots represents 1 gram of dissolved sugar. So, and then also each beaker contains 100 total milliliters of solution. And they want to know what is the percent mass to volume concentration of each beaker. All right, well, starting off with the dilute beaker, we're looking for mass per volume. That's grams. over milliliters. And I think it really helps set up your units. Think about what you're looking for. Think about how you're going to get there. We have 10 grams of sugar particles. When I counted the dots, I counted 10 of them. So that's 10 grams. Each dot represents 1 gram. So that's 10 total grams. We have 100 milliliters of solution. So we divide 10 by 100, multiply it by 100%, and we'll end up with a 10% mass to volume solution for this more dilute solution. There's a numeric value that makes this a quantitative analysis. That helps us a lot. For the darker, the more concentrated solution, again, mass to volume is grams per milliliter. When I counted the dots, I counted 18. So we'll call that 18 grams of sugar. Again, that's in 100 milliliters. So 18 divided by 100 times 100% gives us 18% mass to volume. And again, now we have a way to compare the concentrations of these solutions. I'm not just saying one's more concentrated than the other. I can say this one has about 8% more sugar. All right, in chemistry, we're going to much more often use molarity, capital M. You've probably already seen it. A lot of the labs we do will tell you need to use 1.0 big M. You see that big M? That stands for molar or molarity. Molarity is found by dividing the moles of solute. Kind of sounds like moles, molarity. So dividing the moles of solute by the volume of solution. Make sure you're working in liters. Very important to work in liters for molarity. So the actual definition of molarity is found by dividing your moles of solute by your liters of solution. The reason why chemists prefer molarity versus a percent concentration is that we can work with moles, and moles allows us to go straight into stoichiometry, and we can start using that molarity, those moles, back and forth, and we can work with our problems. We can go from products to reactants, reactants to products. We love moles. This is chemistry. All right, let's take a look at the math for molarity. This time, each dot still represents 1 gram of dissolved sugar, so that hasn't changed, and each beaker still contains 100 milliliters of solution. But this time they're asking, what is the molarity of each beaker? It's really going to help when we do molarity. If you can picture, anytime you see that big M, or the word molarity, or the word molar, don't just picture big M or molar, but picture moles per liter. So let's take a look again at the dilute concentration. Big M, I immediately turn it into moles per liter. These are units I can work with, moles per liter. Again, I still have my 10 grams of sugar per 100 milliliters of solution. I need to convert my grams of sugar to moles and my milliliters to liters. Again, by listing out my variables here, and I don't like that big M. I know it's there, it's what the solution is, molarity, but I like to see moles per liter. It helps me out. We've been going from grams to moles all year long. 10 grams of sugar. Here's the mass of sugar. Off the periodic table, that's 6 carbons, 12 hydrogens, and 6 oxygens per mole. Now I've got my moles of sugar. I have to make sure I'm working in liters. So there's that conversion, 100 milliliters. I'm going to put 1,000 milliliters on top and 1 liter on bottom. There are 1,000 milliliters in 1 liter. Now I've just got my math left to do. 10 divided by 100 times 1 divided by, I'm going to make sure I put these in parentheses here, 6 times 12.011 plus 12 times 1.00794 plus 6 times 15.994. Times all of that by 1,000, and we get 0.555 moles per liter. That's a 0.555 molar solution for the dilute solution here. for the darker solution, the concentrated solution on the right. Again, we're going to go through the same step. I see big M, I see the word molarity. I immediately think moles per liter. Those are units I can work with. That math I can do. 18 grams of sugar. I counted the 18 dots. 18 grams of sugar per 100 milliliters of solution. Again, the same concept holds true. I need to go from grams to moles. I do that here. And then milliliters to liters. I do that there. I crunch my numbers, and I end up with 0.999 moles per liter. That's a 0.999 molar solution. Let's work on another volume to volume example. So the question says, what is the percent by volume? And here we are, percent by volume of ethanol in the final solution when 85 milliliters of ethanol is diluted with 250 milliliters of water. Okay, again, I like to think about it. Volume to volume means milliliters of solute over milliliters of solution. I had 85 milliliters of ethanol. On the bottom here, notice I'm not just doing 250 milliliters of water. Water is just my solvent. My total solution is my solvent plus my solute. So I have to make sure that I add the two volumes together. Again, a percentage is parts of the whole, not just the ratio of ethanol to water, but I want parts of the whole. So I have to include my 85 milliliters of ethanol, multiply the whole thing by 100%, and we get a 25% volume to volume solution. Another example, mass to volume. How many grams of glucose, C6H12O6, are needed to make 2,000 milliliters of a 2.8% glucose mass to volume solution? So this time they're not asking for the concentration. They gave us the concentration, 2.8% glucose. They want to know how many grams I need to get to that concentration. So setting up this problem, question mark gram C6H12O6. I'm going to start with that, and I need 2,000 milliliters of solution. SLN stands for solution. This step right here is my 2.8%. You're welcome to use whatever values you want. You could have used 50 milliliters of solution. You could have put 2,000 milliliters of solution on the bottom if you wanted to. But what goes on the top has to be 2.8% of that solution. My opinion is, why not just use 100 milliliters? It's very easy to know what 2.8% of 100 milliliters is. Any percentage out of 100 is just that number itself. So that 2.8% is written here as 2.8 grams per 100 milliliters of solution. So there's my percentage. Again, you're welcome to use 50 milliliters if you want, but of course you'd have to divide this in half and use 1.4. You're welcome to use 1,000 milliliters if you want, but you'd have to multiply this by 10. Again, I say just use 100 milliliters. Anytime you see that percentage, just put 100 on the bottom. You're allowed to put then that value on top. There's my 2.8%. My milliliters of solution cancels out. The only unit I have remaining then is grams of glucose. So I crunch my numbers, 2,000 times 2.8 divided by 100. I got 56 grams with significant digits. There's only one significant digit in 2,000 milliliters. So I'm going to round that to 60 grams of glucose. How many moles are in 2 liters of 2.5 molar, there's that big M, lithium chloride, LiCl? All right, well, they're asking for moles, so question mark moles is equal to 2 liters. I'll start with that value. 2.5 molar. Again, I see the big M. I don't want to use big M. That's a tough value to use, so I'm going to put moles over liters. That's big M. That value is 2.5 moles per 1 liter. Now my liters are going to cancel out. I'll be left with moles. That's what I'm looking for. Wada bing, wada boom. 2 times 2.5 means 5 moles of LiCl. Another example. Calculate the volume. All right, this time we're looking for liters of 0.25 molar H2SO4 that contains 0.25 grams of H2SO4. Very interesting. All right, we're given molar and we're given grams. We're looking for a volume. So I'm going to say question mark either milliliters or liters. You can choose to do whichever one you want. Now my big hint, I'm going to say this a couple of times. I think I even have it written down in a slide a little later on, is whenever you have the option, start with the unit that only has one, or start with the number that only has one unit. So notice how grams, that's a single dimensional unit. Grams of H2SO4, grams of H2SO4. If I had started with molarity, molar, that has 2 units, that's moles per liter. So I don't necessarily want to start with molarity. Whenever I can help it, I start with the number that has only 1 unit with it. So 0.250 grams of H2SO4. Now I'm not looking for grams, I want to go to moles. So I'm going to convert my H2SO4 into moles off the periodic table. 2 H's, 1 S, and 4 O's is 98.062. Now that I have moles of H2SO4, now I can go to liters, which is good. I'm looking for liters, so I use my molarity. Now notice, I didn't put moles on top. Moles per liter. But I want moles to be on the bottom. I've got moles on top here, and I want it to cancel out. So in order to cancel out that moles H2SO4, I need it on the bottom, and that puts my liters on top. And that's also good because I wanted liters on top. Look over here, the unit I'm looking for has liters on top. So this works out. I know it may look weird. We're used to saying molar is moles per liter, but this is 1 liter per 0.250 moles. It's the same thing. It's kind of like saying we can travel 60 miles per hour, or in 1 hour, we travel 60 miles. We're saying the same thing. 1 liter contains 0.25 moles, or 0.25 moles in 1 liter. We crunch the numbers, and we're going to end up with 0.0102 liters with significant digits. Hey, I've worked through quite a few problems with you. Now it's your turn. 7 problems as homework this evening. Do over the weekend. We'll see you on Monday.